So really, it's not a threat, and also using mutex to resolve these race conditions to protect the concurrent execution from the get-go. It's not an easy task, especially if programmers are asked to do this kind of design. It's very hard to have a proper design that's error-free and also support the max level of concurrency. Really, the main purpose of using multi-threading is to ensure that the tasks can be carried out concurrently to improve the resource utilization, to reduce the latency, eliminate the blocking time. So that's the purpose of using multi-threaded programs. But in this design process, using thread functions and using mutex locks, even semaphores, are not a easy tool that you can always get you the right solution. It requires a lot of thinking behind it. So this makes people think, is the concurrency itself intrinsically hard, or it's some other issues? There are a lot of, in the physical world, concurrency is always there. So there are always people doing things concurrently as individuals. And when you operate machines, drive cars, you do things concurrently. So in the physical world, things seems to go well, even there are a lot of concurrencies. So the concurrency itself is natural. It's the threads that's really hard. When we write threads, we think about sequential process, but these sequential processes, they share a memory. From the perspective of any thread, the entire state of the universe can change between two atomic actions. So that's where the problem is hard, because any thread can change the entire state that every other thread sees. And that's where the problems may arise. Now, with mutex, to be honest, I can't really get the sense from this picture, but although it's included in the picture from the Professor Lee's slides, but I think what he tries to say that using mutexes, it's one way of getting us calm in this turbulent and dangerous environment. At least we have a tool that's within our reach, can help us to resolve some of the issues. But still, it doesn't mean that that's always a beautiful solution. If you don't design the threads in the proper, thinking, if you don't think hard where we should protect the shared variables, where we should avoid race conditions, where we should enforce the orders. If you don't think about this while you're using thread, you will very likely to get troubles because of them. I want to introduce one other solution is to use so-called message passing. Message passing is a bit different from what we saw earlier. What we have here is a producer and consumer function, and we we create two threads. One is perceived user, one is consumer. What we want to do is we will have a producer thread that will send the variables, the new values, to the consumer threads. So one producer is sending and one consumer is always receiving. And there are two, in the main function, the thread create, thread join, or what we saw earlier. But in this thread functions, the main distinction from the earlier design is this send function and this get function. So the send function and get function are the ways we pass the variables between these instances. We don't have really the share variable that we have to protect. Instead, we use send and receive, which underneath they will build a channel to ensure the passing of these variables. Because you can see here, there's no shared variable called a value that you need to pass around. But there's still risk of deadlock and unexpected non-determinism if we don't do it properly. So that's why I want to show you the send and the get function here. Send on the left side is the send function, on the right side is the get function. So what we are trying to do is using the send function, the producer can send new messages, new variables, to the consumer side, or consumer side we use get function to retrieve the data. Very similar design inside the send, where you can see we create a linked list. Different from earlier the linked list. On this linked list, we use the variables itself, the messages, as the payload. So every node carries a new message, new value, and being added to the end of the linked list. And let's see, we have a few things, so mutex lock, mutex unlock, that's where you will protect the this critical section. And the other thing we have here is this condition signal and pthread condition wait, pthread condition signal. Now this here is something new that we should talk a bit more about. This pthread condition is essentially a semaphore that's used here to indicate what the variable is gonna be, or which thread should be waiting, or which thread should proceed. So let's use this get as an example. So we first will try to see, so get function tries to find new values from this linked list, because the send function will put new values on this linked list. So the get function, as you can see here, we're trying to get the first payload, that's the message from the head, from the first node on the linked list, and then we move on to the next one and then free the element. But before we do that, we'll have to do one thing, that is to check the size. We'll check the size, and the way we check it is to say, okay, do we have size equal to 0? Okay, if we have size to 0, that means we don't have any new message on the linked list. We will call this pthread condition wait. Now it takes two arguments. First is the sent, that's one of the condition variables, and the next one is the mutex. And this the mutex is the lock that we acquired earlier. Now this gets interesting because normally if you do lock, nobody else can get this lock until release. So that's what the unlock is for. But with the pthread condition wait, what it does is to it will release the lock momentarily, and it will be waiting on this send on this condition variable. So when this mutex, this lock is released temporarily, so there's a chance that the send function will be able to get this lock. And that's really when the send message is called, the send function is called, indicating the producer wants to send a new message onto the linked list. So in that moment, this lock will be acquired, and then this send function will be able to put a new message on the linked list. Then it will signal that back to this wait condition. So this part of the code, this get function will be waken up, and we will this thread will be waken up, but it will still be basically waiting on this one until this unlock API is called. So this API will return after this mutex is unlocked, because this thread is being waken up, and also this mutex is acquired again after the send function released that. And the good news here is the size will now be greater than 0, because the send function just increased the size after putting the new message on the linked list. Okay, so this get function will move on. It will be able to get the payload from the first node of the linked list, and then free that and decrement, then unlock. So in this way, send and get function can operate fairly efficiently using a shared linked list, but avoid deadlock on it. Okay, so we introduced one solution with the message passing, but really the takeaway message here is non-trivial software return with threads and semaphore and mutex is incomprehensible to human beings. You really have to try hard to understand these nuances of concurrent execution using threads, and how we can apply mutex and semaphores to make them more efficient and avoid deadlocks to find a good solution. Let me see, what time is it? So let me just proceed to finish the next few slides.
Do threads have sound foundation?
Pardon me?
That was a mistake. I was muted, sorry.
Okay. All right, so threads. So let's see a little bit more about threads. So the question was, do threads have a sound foundation? So is the way we define threads a reasonable definition, and why it's so difficult to make it work properly? So this is the Pizza Tower, I think in Italy. This whole enterprise is held up by a few threads here. I think just for precautions. So it's really what we see on the thread. So what's the problem? The model of computation is like this. We're dealing with data, so we can abstract them with 0 and 1s. And we have a set of finite sequence of bits, and we do computation. So we apply this function f, and f takes this set b as an input, and the output is another set of based on B. And we can have compositional functions, and we can apply multiple functions. You can do all kind of operations, signal processing to change this 0 and 1s. And the programs that we design specifies the composition of these computations. So another way to understand what we are trying to say here is that we have instructions. Instructions will operate on variables, registers, and you may have multiple instructions that you will apply, and then eventually you have the whole program. So threads actually augment on this model to allow concurrency. But this model does not admit concurrency gracefully. The basic sequential computation is what we are used to write programs, and it's always the case. When you learn programming, you don't learn parallel programming at the beginning. So you always think programs are a sequence of instructions being executed from the beginning to the end. So what this means is you have an initial state, B0, and then at every step, you will go through one of the functions in the sequence, and you will apply this function n on the earlier value of B, and you get the new value based on the initial value and the function that you define. So if this is a 0, you will, let's say this function is inverse function, then you'll get 1. So depends on what you have in an instruction, but you always do this. And eventually you have a final state, B subscript n, if you have n instructions. So formally, the composition of a computation is a function composition. When you have threads, you are in trouble. This is really what happens. So this blue thread got suspended at some point, and its goal, or at that point, it states is Bn, or it's about to execute Bn based on Bn minus 1. But because this instruction was suspended, another thread can be scheduled, and the other thread will do a lot of things. And one thing could be changing the state. That means when the thread 1 resumes execution, it's now seeing Bn minus 1. It's possibly that becomes B prime n minus 1. So this state here, or this input variable here is now different because the injection or interference or interleave the concurrent execution of another thread. So that's where we see the complications come from. We have the threads that we can easily use to share variables, and because the threads can execute concurrently, they may change the state, and then we have to deal with that. So really the problem is because threads are wildly non-deterministic, and the programmer's job is to prune away the non-deterministicism by using constraints or execution order. For example, you can use mutexes, and also you can use shared data limiting shared data access, such as using object-oriented design. There are incremental improvements throughout the years. Here's just a short list of those. You can use objects to encapsulate the data accesses. You can use enforce coding rules, acquiring logs in the same order and releasing them subsequently. You can use, for the database, you can use transactions to ensure atomic operations. You can use MapReduce to divide the bigger problem into smaller ones, then aggregate the results. You can use formal verification to do model checking to prove your program will behave correctly. So there are a lot of different things that people have been trying to resolve the problem or address the challenges in using multi-threaded programs, designing multi-threaded programs.